glass. Go ahead, Diane.
Okay, thank you. So this is work that I've been doing with Mac Rutherford, Steve Jacobson, Eric Gowrie, Alberto Saul, and Sylvia Monique Thomas. So like we've been talking about this whole workshop, the moon was thought to be dry previously until Solubility in 2008 measured water by SIMS in the lunar volcanic glasses. Prior to this, Sato proposed in 1976 that carbon would be the main volatile species. Specifically, a CO-rich gas can be used to explain the fire fountain eruptions that produce the lunar volcanic glass beads. There were a couple of studies that were done looking at FTR and Raman spectra of both natural and experimental glasses, but were unsuccessful in determining any carbon species dissolved. However, based on our SIMS data,
I thought we were plugged in.
Oh,
no, sorry.
Oh, that's just, okay. However, the SIMS data shows that we have up to 40 ppm water dissolved in the glasses, and so therefore we should be able to see how hydrogen is dissolved in the melt using spectra. Carbon is too low in concentration, so probably not seen in spectra. So I'm going to be presenting experimental work on carbon solubility and speciation in synthetic green glass composition, as well as presenting FTR and Raman spectra on natural lunar glass samples and their related absorption coefficients. So first I'm going to be presenting some of the work that we just recently had published in PNAS, where we synthesized a lunar green glass composition, and we did this in graphite capsules that were then enclosed in platinum capsules. So these are graphite saturated experiments with water accessible to the system. And we ran a series of experiments at various pressures, as you can see by this diagram. And then we also used 3 different buffering techniques so that we were able to explore a range of FO2. And so this way we could look at the FO2 range that we think is applicable to the lunar mantle. And for the following plots, what I'm going to be showing is we're going to have the same color scheme. So if you see anything in red, that's going to be melts that are more reduced, so FO2 is less than iron wustite minus 0.55, and anything in yellow or yellow-orange is going to be more oxidized, so above iron wustite minus 0.55. So like I said, all of these experiments were done in graphite capsules, so we can look at what the carbon solubility is. And you can see this on this plot, which is carbon versus pressure. And one thing you will note is that we see 2 different trends for solubility, one for the oxidized melts and one for reduced. So at a given pressure, you can see that the oxidized melts will dissolve twice as much carbon as the reduced melts. And so this is important when we want to think about when these melts will reach saturation and produce the gas phase, first gas phase. So basically, the reduced melts will form a gas phase deeper than the oxidized melts, and so this plays into how efficiently you can degas in the process. So we do see these 2 trends, and one of the questions we had is, well, why is this? And one of the ideas we had is, well, maybe it's speciation. And for this, we looked at both FTR and Raman spectra to determine how carbon was dissolved in these melts. So what I have here is Raman spectra for the experimental glasses. Again, red is reduced, yellow-orange is oxidized, and you'll note that there's a peak at 2110 in the reduced glasses. You don't see it in the oxidized glasses, and this is due to iron carbonyl. And so this is really a new carbon species that we need to think about when we want to think about how carbon is dissolved in reduced lunar melts. And so this also goes along with, it sort of confirms Sato's initial hypothesis that CO can be really important in this. But we also know from Alberto's work that we also have to consider hydrogen. And so if we look at the higher wave number region for the Raman spectra, you can see that we also have some methane dissolved in the reduced glasses at 2900. But you can see from the peaks it's very minimal, and this is consistent with Hirschman's group's work out of Minnesota, where they found that the amount of methane that you can dissolve is actually minimal. So basically what we have is most of our carbon is dissolved as this iron carbonyl. In terms of other hydrogen species, we see that most of the hydrogen is dissolved as hydroxyl or molecular water, and this is seen at the 3550 total water peak, and you can see that this is present for both oxidized and reduced melts. We do have one hydrogen peak that we did find, molecular hydrogen, but this was for a glass that had a lot of water dissolved. So it may play a role, but it's not going to be the main hydrogen species dissolved in these melts. We also then used FTIR to then determine how carbon was dissolved in the oxidized melts, and we find that carbon is dissolved as carbonate, as seen by the carbonate doublets at 1430 and 1530. And this is consistent with previous experimental work that has looked at more oxidized systems for terrestrial basalts. But this figure is also a nice summary to show that we do have two different carbon species that we need to consider in terms of the lunar melts. And we can actually plot this up then where we can show that carbon speciation is a function of FO2. So we have this transition from iron carbonyl as your main carbon species dissolved to carbonate, and this transition occurs at iron wustite minus 0.55. And this is really important because this is right in the middle of the FO2 range that we consider for the lunar mantle. So if we want to talk about how carbon is dissolved, we really should consider both of these options. And you'll also note from this figure that this transition does occur in a range that we should consider for other planetary bodies as well. So this experimental work is a good way for us to understand how carbon is actually dissolved in these lunar melts, since carbon is too low in concentration to really look at in the spectra. But like I said, we can look for hydrogen, and based on the experiments, we should expect to see most of the hydrogen dissolved as hydroxyl or molecular water. So we can then look at some of the natural samples to see if the experiments if we can confirm what we see in the experiments. And so we looked at orange, green, and yellow glasses, and so we did both FTR and Raman, as well as electron microprobe and SIMS on these. And so here we have FTR spectra of the green, yellow, and orange glasses, and you can see that they're color-coded for each composition. And each composition is paired. We have the glasses that we synthesized in the lab on top, as well as the natural samples on the bottom. And you can see that for each composition, the natural and synthetic match very, very well. The only difference we really see is that we see this water peak at 3550 in the synthetic glasses. And again, that's because we dissolved much more water than what we would expect to see in the natural samples. We can also look then at the Raman spectra. Again, we have all three compositions and the coupled natural with synthetic glasses as well. And you can really see how nicely they match. And so if we want to try to tease out any sort of water peak in the natural samples, it's good to know that our synthetic are a good representation, and so we can use these to better understand how to handle the natural samples. So in order to tease out this water peak, what we'll need to do is do some sort of baseline correction. In order to do this, we looked through all of our experimental green, yellow, and orange glasses to come up with a methodology in terms of how we should best baseline correct the water peak. And you can see from this plot here, this is a synthetic green glass, and you can see the asymmetric water peak at 3550. And we found that a linear baseline is the best way to correct the spectra. And you can see that from the red dashed line. And so we would do this correction between 2750 and 3670. And so once we've done this, we can also then come up with the absorption coefficient, which is required for calculating the water contents for these glasses. And we would be using the equation that you see there, that's Beer-Lambert law, and the absorption coefficient is the epsilon. And this coefficient is a compositionally dependent value, and so we were able to determine this for all three compositions. And so this is a table that I've compiled the absorption coefficients that we've calculated for the green, yellow, and orange glasses for both carbonate and water peaks, and compared this to a terrestrial Morb glass. And what you'll see is that the lunar absorption coefficient values are lower than the terrestrial coefficients. And this is significant in terms of if we want to calculate how much water there is using Beer-Lambert. the equation down at the bottom, using the lunar glasses will give us 25 to 55% more calculated water dissolved than if you were to use the terrestrial absorption coefficients. And like I said, these are compositionally dependent, and this is really shown well in terms of Mandeville et al. 2002, their study on andesitic compositions where they looked at iron-free versus iron-bearing. And you can see from the water coefficients that as you increase the amount of water in your system, iron in your system, then the absorption coefficient decreases. And this is consistent with what we see for the lunar glasses, which have much higher iron contents than terrestrial values. So now that we have this consistent methodology to baseline correct the spectra, we can actually tease out water peaks in the natural lunar glasses. And so these are two green glasses that we've teased out the total water peak here. And we've used the absorption coefficient to calculate how much water there is dissolved with FTIR. And you can see that this matches very well with the SIMS data. So this is really nice that we can actually then connect the natural data to our experimental samples and see that we can actually tease out these water peaks. So to wrap up, with both the natural and experimental data that we now have a better understanding of how carbon and hydrogen is dissolved in the lunar melts. Carbon will be dissolved as a carbonate for oxygen fugacity greater than iron wustite minus 0.55, but if you have a more reduced melt, you will mainly have iron carbonyl dissolved and possibly some methane, but mainly carbonyl. For hydrogen, most of the hydrogen will be dissolved as hydroxyl and molecular water, and it doesn't matter what the FO2 is, that will be the main volatile species based on our experiments. And you could have some methane if you have more reduced melts, and you could also have some hydrogen as well, but those will not make up a majority of the hydrogen species. Like I said, it'll mainly be hydroxyl and molecular water. So we've been talking a lot about water, but it's also important just to keep in mind that carbon can also play an important role and should be considered for magmatic processes and lunar evolution. So thank you.
Thank you, Diane. Looks like we've got Larry typing a question. Are there questions out there for Diane? Okay, so Larry says that we have called upon iron carbonyl as the manner for iron to move around in meteorites.